Hey, what's up, guys? This is Sheng here again. So this time on 1802, maximum value at a given index in a bounded array. Okay, so you're given like three positive integers, n, index, and the max sum, and you want to construct an array nums, right? That satisfy the following conditions. So the length has to be n, and each number is a positive integer, and the absolute difference between two adjacent numbers is either equal or smaller than 1. Okay, and the sum of all the elements does not exceed max sum. And at this index, the number is maximized. And you just need to return the maximum numbers on this index. Okay, so for example, we have this kind of n is equal to 4, index is 2, max sum is 6. Right, so the maximum we can get is 2 in this case. I think this is because we have 1, 2, and so okay. So the index 2, I think it's 0. Oh yeah, it's a 0 indexed. So that's why we have that's why they have like two possible solutions. Maybe 1, 2, 2, 1, right? 1, 2, 2, 1. So that's why this one is 2. So similarly for this one, so we have total we have 6. Basically we have 6 numbers, right? For the second one, we have 6 numbers, and we're trying to maximize index 1, which is this one, right? And the total is 10. So the answer for this one is 3. And why is that? Actually, so one of the solutions is like this. So basically for 3, and then we have 2 on this one, right? And we have 2, 1, 1, 1, right? That's how we get this 10, because I think the total for this one is what? It's like, I think we have, this is 8. Yeah, this is 10, right? So basically this one equals to 10. Cool. So to solve this problem, actually, you know, so for this one, since we're trying to maximize this number, right? We should just try to maximize this number, and then still we satisfy this kind of this conditions. I think one of the observation we can make is that we should make here is we should make is here as long as we fix like this kind of numbers here, since we want this sum as smaller as possible. Basically, as long as we fix values at this index here, we will always try to decrease on both left side and right side. That, for example, if we fix this one to 3 here, right? Of course we can make this one 3, and we can also make this one 4, right? So basically 2, 3, or 4. 2, 3, or 4, they're all satisfied this condition, right? But we want to choose the smaller one, the smallest one, which is 2, because we want to minimize the total sum, right, of this kind of array. That's why we always choose the smaller one, right? So similarly on the right side, that's why what I'm saying that as long as we fix the number here, we always try to decrease the number on both left side and right side. And then that leads to us like a binary search solution, right? where we binary search this value directly, right? And every time when we have a fixed nums index here, we try to use a greedy approach to calculate the smallest sum, right? Which satisfy all the orders of conditions, and if that's the sum is within this max sum range, then we know, okay, so that one is satisfied. We can just move our cursor basically to the right side, right? Otherwise, we go to the left side. Okay, cool. So, and then that's lead us to this kind of binary search solutions. So which means that for the left we have 1 because all the numbers they need to be positive integers, and then the right side I'll just use the max sum to be the upper bound, and then to search the biggest numbers we have a template, right? So while L is smaller than R, then we have middle equals to L plus R minus L, then divided by 2, right? If helper, right? So I'm going to call it helper functions. If the middle one is true, right? It means that we should go to the right side. Since we are calculating the maximum values, right? It means that if this one is true, we're gonna move this middle one, assign this middle one to the left. Otherwise, we assign the middle one -1 to right. Okay, and then in the end, I return left, right? So this one means that since the L could be the answer, basically we're trying to move the lower bound to the right as much as possible, right? Oh, and since we are doing like this kind of L, the lower bound equals to middle, we have to do a R minus L plus 1. I think I have already talked with this one a few times, basically. So every time when you have like a left equals to middle, you need to do L minus L plus 1. This is to make sure, when we have like L equals to 3 and R equals to 4. If we don't do this L minus L plus 1, if we don't do the plus 1, basically we'll end up to an infinite loop. Basically the L will always be 3, and we'll never exit this while loop. Okay, cool. So this is a template to calculate the maximum values by using the binary search, right? And then the rest is just like to implement helper functions, right? And so to calculate helper functions is a little bit complicated. Like I said, if we have like this kind of integers here, right? Let's say we have a middle values here, right? We have a middle value here. Actually, this is 3, right? So if we have a 3 and then we have 2, 2, 1, 1, 1, right? So if the length of the left side is smaller than the middle values, right? Actually, we're not getting everything, right? Basically, it will stop at some place. And if the length on the side is greater than the value itself, like I said, basically the value will be decreased to 1, and then it will remain as 1, right? So at least that's how the way I did it was since we know the total values from the middle to 1, right? Which is the n times n plus 1 divided by 2, right? That's going to be the total values if we decrease this middle to 1. And then by comparing the length on the left side and on the right side, I can either subtract the missing part, or I the missing part in what is 1 in this case, right? By subtracting the missing part, or by increasing, or by adding the remaining ones part, right? If basically it means that if the length is smaller than this one, we need to subtract the missing part, and if the length is greater than 3, we need to adding the remaining ones. Okay, so that's why for the total, right? So the total we have this n times n plus 1 divided by 2, right? So I think I'm just that's why I have like another helper functions. I'll just call it accumulate, right? With n. This one I simply return the n times n plus 1 divided by 2, right? So, and the total is the accumulate middle, right? And then for the left length, right? So I call the left length equals to the index plus 1, right? Since the index is it's 0 based, right? So this index is 1, but the left length, including the middle itself, is 2. That's why I do this one, right? And then the right length equals to n minus index. This one we don't need to subtract 1 because n is 1 based, actually, right? And then I have a left offset, right? I call it left offset equals to right offset equals to 0, because the offset could be a negative or it could be positive, right? Okay, so if the left length is smaller than middle, it means that we need to subtract the missing part, right? Which means that the left offset equals to a minus accumulate, right? Middle minus left length, right? This is the missing part, and we also need to do the accumulate parts, right? Because let's say we have 5 and 4, right? Basically, actually we're missing 1, 2, 3, right? So this is the part we're missing. That's why to get the 4 and 5, at least that's how I do it, right? So we have a total here, we need to subtract the 1, 2, 3, which is the middle minor, subtract the left length. Okay. Else, right? Else the left offset means that the left length subtract middle. Okay. So this one means that how many ones, right? How many remaining ones we need to add to the total value, right? That's going to be the left length minus subtract middle. And same thing for the right part. I'll just copy and paste here. So we have a right right length, and we have a right offset, right? Okay, and then so the answer is that the total, right, times 2, right? For both the left and the right side, and then total plus left offset, right? And then plus total plus the right offset, right? And then subtract middle, right? Because this is the middle, right? So this is the left side and this is the right side, and then we count this middle one twice. That's why we need to subtract this middle. And then we simply return if the answer is either equal or smaller than the max sum, right? if it's smaller, by using this kind of greedy approach, it means that it's true. Otherwise, it's false, right? Yeah, I think that's it, right? I mean, if I run the code here, accept it, if I submit, uh, let me see. Seems like something is wrong here. So we have this one. Oh, I see. I think it's because the uppercase, right? I think there's a uppercase S. Yeah, yeah, cool. Yeah, and yeah, so and the time complexity, right? So we have uh log. Yeah, so here we have log n, right? Where n is the 10 to the power of 9, and inside the helper functions here, I think it's this is O of 1 actually. Yeah. So this is O of 1, the helper function. So I mean the total time complexity is the log n basically. Yeah, I think that's it, right? I mean it's just like very classic binary search solutions where we fix the index values, right? And then we greedily calculate this the total sum, right, of the entire array by using some of the math formula, and then a little bit trick of the, at least I use the offset, right, by comparing the length of the left side and right side. I mean, I'm pretty sure there could be other solutions, but anyway, this is how I did it. Okay, cool. And I think I'll stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.